Welcome to the last section in Chapter 11. Today we're going to be talking about areas and volumes of similar solids. First thing we're going to be talking about is figuring out if solids are similar or not. The question is, are the two rectangular prisms similar? If so, what is the scale factor of the first figure to the second? The way we're going to do that is we're going to look at the corresponding side lengths. So for this first one in A, we've got 8 and 10. We've got 3 and 4, and we've got 5 and 7. So if they are similar, all three of these fractions should be the same. And if you look at it, 8 divided by 10 is 0.8, 3 divided by 4 is 0.75. I don't even have to do 5 sevenths because I know that these aren't the same already, so they are not similar. For the second one, again, we look at corresponding sides. We've got 10 and 15, so 10 over 15, 4 over 6, and 6 over 9. Okay, if we simplify these down, looking to see if they're equal, 10 over 15, I can take a 5 out of both. 4 over 6, I can take a 2 out of both. 6 out of 9, I can take a 3 out of both. For all of them, I get 2/3, and so yes, they are similar, and my scale factor is 2/3. Theorem 1112, areas and volumes of similar solids, tells us that if the scale factor of two similar solids is A to B, then we wouldn't be able to find the ratio of their surface areas to be A squared to B squared, and the ratio of their volumes would be A cubed to B cubed. So just a really quick example, if our scale factor was 2 to 3, the ratio of the surface areas would be 2 squared to 3 squared. The ratio of their volumes would be 2 cubed to 3 cubed. And so that's how we would be able to use it. And we can go from scale factor up to volumes, or if we are given the volumes, we can work our way back to scale factor as well. So with our first example here, we are told that these two cylinders are similar, and they want to know what the scale factor of the smaller cylinder to the larger one is. Now what we are given is we are given the volume of both. So if we were to find the fraction for that, and we want to do smaller to larger, so we're going to put the smaller one on top, 64 pi over 125 pi. And we're going to simplify it down as far as we can, but really the only thing we can do is cancel away the pi's. So we've got 64 over 125. Okay, now if you remember, scale factor is A to B, and volume is A cubed to B cubed. So if we are starting with volume here, to work our way back here, we have to get rid of the cubes. So we would do a cubed root. And the cubed root of 64 would be 4, the cubed root of 125 would be 5. So our scale factor here would be 4/5, or 4 to 5. Same thing with the next example. We've got two square prisms that are cylinder. What is the scale factor of the smaller one to the larger? So again, smaller will go on top, larger will go on bottom. If we simplify that down, we can take a 6 out of both the top and the bottom, giving us 25 over 49. Now, when we're given surface area here, remember, scale factor is A to B. Surface area is A squared to B squared. So we're starting here and we're working our way back. So now, instead of doing the cube root like we did in the last example to get rid of volume, we're going to do square root here to get rid of the squared. Well, the square root of 25 is 5. Square root of 49 is 7. So our scale factor would be 5/7, or 5 to 7. Our next example, we talk about the lateral area of two similar paint cans are 1019 square centimeters and 425 square centimeters. The volume of the smaller can is 1157 cubic centimeters. They want to know what the volume of the larger can is. So what we need to do first here is we have an area ratio. So we need to go from area ratio back to scale factor, and then from there we can go to volume. Okay, so if I find my area ratio, okay, 425 over 1019, Okay, this is my area ratio. Now I want to go to a scale factor ratio. Well, to go from area to scale factor, again, we square root. So I'm going to be doing the square root of both of these. Now, we're not going to get very good numbers, but we're going to round it to the nearest whole number to make things easier. The square root of 425 is going to round to about a 21. The square root of 1019 is going to round to about 32. Okay, so this is going to be our scale factor ratio. Then from there, I need to go to my volume ratio. Well, to go from scale factor to volume, I'm going to cube everything. So if I take each one of these cubed, 21 cubed is 9261. 32 cubed is 32,768. So now they give me the volume of the smaller can. So when I set these equal to each other, I put the 1157 with the smaller number. And then I'm going to cross multiply and solve. So if I take 1157 times 32,768, I get 379,12576. And that's going to be equal to 9,261 times x. So then I divide 9261 from both sides, and I get that x is about 4,094. So 4094. That's going to be my volume. Our second example, we've got the volumes of two similar solids are 128 cubic meters and 250 cubic meters. The surface area of the larger solid is 250 square meters. They want to know what the surface area of the smaller one is. So just like we did before, we start with our ratio. This time it's going to be a volume ratio. And we've got 128 over 250. And the first thing I want to do is I want to simplify this down as far as I can. I can take a 2 out of both of these. So really, my volume ratio is going to be 64 over 125. And what I'm going to do is I'm going to work my way back to scale factor. Now, to go from volume to scale factor, we're going to do a cubed root. So the cubed root of 64 is 4. The cubed root of 125 is 5. So my scale factor is 4/5. From there, I go to my area ratio, which means I need to square my scale factor ratio. So 4 squared is 16. 5 squared is 25. My area ratio is 16 over 25. What I'm going to do next is they tell me that the surface area of the larger one is 250, so I'm going to put 250 on the bottom, x on the top, and I'm going to cross multiply. So I'm going to get 25x is equal to 16 times 250, which gives me 4,000. Divide both sides by 25, and I should get 160 square meters. For our next example, we are told that a bottle that is 10 inches high holds 34 ounces of milk. Okay. The sandwich shop shown at the right, now there's no picture here, but the only thing you really need to know is that it's 480 inches high, is shaped like a milk bottle. To the nearest 1,000 ounces, how much milk could the building hold if we needed to fill it in? Okay, so what we're going to do first is we're going to do the scale factor ratio. So the bottle is 10, and the building is 480. Okay, I can simplify that down to 1 over 48. This is my scale factor ratio. So that is my scale factor. Now from there, when we're talking about how much milk something can hold, that's a volume problem. So my volume ratio I can get by cubing my scale factor. Well, 1 cubed is still going to be 1. 48 cubed is 110,592. Okay, so here is my volume ratio. Now, what I'm going to do with that is the small bottle holds 34 ounces of milk. So I'm going to put 34 over x. I'm going to cross multiply, And whatever I get for 34 times 110,592 is going to be my answer. And I get 3760128. So about 3,760,128 cubic ounces is what that building is going to be able to hold. Our final example, an office supply store sells paper clips in small and large boxes. A small box holds about 220 paper clips. The large box is formed by doubling the dimensions of the small box. So that piece of information is very important. Doubling the dimensions. About how many paper clips should fit in the large box. So again, we're going to find our scale factor ratio. Now, since the large is found by doubling the small, our scale factor is going to be 1/2. So small is going to be the 1. The 2 is going to be the large because we're doubling it. Now, again, we're talking volume because we want to know how much it holds inside. So to get to our volume, we cube everything. 1 cubed is still 1. 2 cubed is going to be 8. So our volume ratio is going to be 1/8. Now the small box holds 220, so I put 220 over x. Cross multiply, and x is going to be what I get when I take 220 times 8, which is going to be 1,760 paper clips.